All right. Hi, everyone. Thanks for coming. So, yeah, I'm Travis, one of the contributors on the Verus project. And today I'm going to tell you about verifying a memory allocator in Verus. So first of all, Verus is a deductive verification tool for Rust that supports verification of memory safety and functional correctness properties. It has a language for writing specifications, and Verus will prove that your code meets your specifications, possibly with help of developer-written proofs. Now, it might be kind of interesting that I say we verify memory safety properties, since we are talking about Rust, which already has good memory safety guarantees. But of course, those don't always hold if you're using unsafe code, for example, and that's going to be particularly relevant for the topic today, which is memory allocator. So for memory allocators, the particular one we're going to be talking about is a design called mimalloc, which is from a few years ago out of Microsoft. And as I understand it, it was mostly designed as a backend for Lean and Coca, which use lots of reference counting. And so the memory allocator was designed specifically to be optimized for that workload, but also has generally good performance across the board. By the way, I'm not particularly associated with the developers of mimalloc. I just chose this one as sort of the template for the design of our verified allocator. So obviously, mimalloc was written in C, and so of course we're not going to be verifying the original mimalloc. It would be very hard to verify C code using a Rust verification tool. So what we're actually doing is we're writing a new memory allocator, sort of using mimalloc as a design template, written in Verus/Rust. And the project is currently a work in progress. Although it is pretty far along now. Our memory allocator does run. You can call it from Rust, either more Rust code, which is also verified in Verus, or you can call it from unverified Rust. You can also override the system's memory allocator, which demonstrates that sort of we're not sort of inadvertently having a cyclic dependency on some other allocator. There are some limitations. It doesn't support aligned allocations. It doesn't support realloc, which is a function that sort of lets you resize allocations. There's also a size limit to what you can allocate. And the proofs of correctness for the parts that we have written are also in progress. It's very close to being done now, but it is still something I'm actively working on. Okay, so this is the project I'm going to tell you about in this talk. I'm going to start, before we talk about memory allocators, I need to tell you quite a bit about how Verus works. So I said before that Verus lets you write specifications for code, and usually this takes the form of these preconditions and postconditions given by requires and ensures. So this particular example is a function that computes a Fibonacci number, and you can see it has a precondition and a postcondition. The precondition says that the sort of input integer n needs to be such that the nth Fibonacci number fits in the U64. And then the postcondition says the result is equal to the nth Fibonacci number. Okay, and for writing specifications, Verus supports a whole functional specification language that sort of looks like Rust and is in fact actually type checked by Rust. So here, for example, you see the definitions of 5.0 and fits in U64. So this is just a little example of writing a specification in Verus. When you zoom out to like sort of the top level, Verus in general consists of Rust code plus a specification like I just showed you, and also proof code. The Rust code obviously is just Rust. It gets compiled with Rust C. However, the Rust code together with the specification and proof can be processed by Verus, where it will basically use an SMT solver to try to show that all your proofs are correct. And if it succeeds, it shows that the code meets all the specifications. If something goes wrong, it will print an error. And in a few slides, I'll give some examples of like what kind of errors can come up. Okay. That's the very high level picture of Verus. So when it comes to the question of verifying a memory allocator, there are some particular challenges, and actually these are challenges sort of that we'll encounter even for unverified Rust. When we implement a memory allocator, we can't use our favorite tools like box, RC, and vec because those assume an allocator, right? Instead, as memory allocator developers, we're responsible for sort of managing the address space ourselves, and as a result, we're probably going to be using lots of unsafe code. And so in order to explain how we're going to tackle this challenge, I have to explain how Verus lets us handle memory permissions. So if you've been to any of the prior Verus talks, you might have seen us talk about this p-pointer API we have, which lets you work with memory permissions. So the p-pointer stands for permissioned pointer, basically. And however, the p-pointer API relies on the sort of global allocator. So it's not really sufficient for building our own allocator. Okay, so we're going to have to tweak this system a little bit to get something that will help us verify an allocator. But before I talk about that, I'm going to explain how the original p-pointer API works. Okay. Now, the p-pointer API basically has two objects. One is called p-pointer and the other is called points to. And p-pointer is actually, it's really just a pointer. In fact, even having a different name for it is kind of pointless. It's really just a pointer to a t. And the points to is the special ghost object that represents a permission to read or write from some allocation that one of these pointers points to. Okay, and the points to is called a ghost object because it's the object is only around for proofs. It's not going to be correspond to an actual runtime object. So you can think of it as being like a zero size type. The implementation is actually a little more elaborate, but if you think of it as a zero size type, you'll get the right intuition. Okay, and I'm going to explain how p-pointer and points to work using a concrete example. So because this part's pretty important to understand, so I'll go into a lot of detail here. So what I'm going to do, so over here on the left, I'm going to show some code, and over on the right, we're going to visualize what's going on when we run the code. So the first line here is we're going to call the new function, which is basically alloc. So it's going to allocate something on the heap, and it's going to store the value 20 there. So you can see on the right, we've allocated at this pointer address 1004 and put the value 20 at that address. And we also obviously return the pointer, which gets set to the variable p, which is in the stack. Okay, so this is what's going on, like actually when you run this code. However, you can see the p-pointer also returns this points to object, and it's in this little tracked thing, which is a special Verus thing that basically means the points to is a ghost object. But otherwise, you can ignore it. So the points to object again doesn't really exist, but Verus does see the points to object. So in Verus's perspective, the points to is very important because the points to actually shows that the pointer points to the value 20, right? And by the way, the name points to comes from separation logic, if you didn't make that connection. Right. So yeah, so that's basically what happens when you do an allocation. If you were to write to P, say here we're writing 5 into P, you can see it gets updated up on the heap. That's what happens in real life. And in Verus's perspective, it's actually the points to object that's getting updated. The value pointed to by the pointer is getting updated to 5. Okay. If we were to perform a read from the pointer, here we're reading into the variable y, we can see obviously 5 gets copied from the heap into the stack. And in Verus's perspective, the value from the points to gets copied into this new variable y. Okay. And if you were to then go ahead and say assert that y equals 5, Verus would say, yeah, that checks out. That checks out for any possible execution. Okay. Now, there's something important to point out here about why this whole system is sound. So if we take a look at this one line, p.write, we can see that it takes points to as a mutable reference, okay? essentially, because it requires unique mutable ownership of points to, this basically enforces that you actually have the permission to write to P. It both prevents like use after free bugs, and it also prevents data races because the ownership has to be unique. However, there's also something else being checked here that's kind of happening in the background, which is that Verus is checking that the points to value actually correctly corresponds to the pointer, right? It checks that you're not using some other permission to some other pointer to access P, okay? So, and this is obviously crucial for the whole thing to be sound. So basically, in conclusion, what this means is that memory and safety is actually ensured by the combination of ownership checking, which Rust-C does, and Verus is checking that sort of the preconditions to p.write holds. Okay. All right, are there any questions right now? I don't know how to see if there are questions.
I have a question, Travis. Can you say more about the separation logic that you, this is Jonathan. Can you say more about the separation logic that you have underneath? You alluded to it on the previous slide.
Oh, yeah. So when I alluded to it, it was really just by analogy. The points to is meant to be analogous to the separation logic's points to assertion. The points in separation logic, you have this points to like proposition, like usually written like L points to V or something, which says that the location L points to the value V. And our points to object is the same. It has the same information as it has a pointer and has the value being pointed to.
Okay, but you did not mean to say that you have separation logic like reasoning facilities. You just wanted to say it's kind of like a points to predicate.
That's right.
Okay, so what is your memory reasoning like then? What are your axioms or reasoning principles to talk about aliasing or things like that? Do you have any at all?
So well, points to is the main like sort of reasoning tool we have for doing that. Can you be more specific about your question?
I can write to you afterwards. I don't want to derail your talk.
All right, that's fine. Okay. I actually okay. I also prepared a little demo of this in action, which I want to show just to sort of how do I get out of just to sort of to drive that last point home. So I prepared two examples, each of which shows an example of doing something wrong. So in this example, we perform an allocation. We write to it, that doesn't really matter. Then we perform a deallocation. And then we're going to try to read from the pointer. So this is a read after free bug. So this is a bug. And if you were to run it through Verus, you can see that it gives you an error about perm. It basically says perm is sort of moved away here. So perm is the points to object. So perm is moved away here, and so you can't use it here. Okay. And this error message is just straight from Rust-C. So this is Rust-C's normal lifetime checking. Here's another example, which is basically the other kind of error. So here we do two allocations. We allocate P, we allocate Q, then we deallocate P, and then we try to read from P, right? But this time, we attempt to sort of justify this read using the permission for Q, okay? So this is another read after free, but we're trying to like cheat the system. And so this is not going to be a type error. This is going to be fine. We do have perm Q. Rust is not going to complain. But if we run it with Verus again, Verus will give an error of a precondition. It'll say you can't call p.read here. You can't call this because the permission does not correctly correspond to the pointer. Okay. So all that was just illustrating this point again, that memory safety is ensured by both of these things together. Okay. All right. So let me the slide. Oh.
Travis, I think Daniel has a question for you.
One quick
yeah,
question.
go ahead.
Just, sorry, I arrived a few minutes late, so maybe you already covered this, but what exactly does Verus offer? So, like, what does it do? Does it give you a way to specify your code, or do you just, what do you actually check? What are your reasoning? What level of Rust do you cover? So
Right.
what
So
guarantees do you give, basically?
So you can basically show arbitrary preconditions and postconditions. Like, were you here for this slide?
I was, yes.
Oh, okay. Well, I mean, yeah. So usually this is the kind of thing you show. Like, you want to show that, like, the answer is correct, right? For the memory allocator, and actually at the very end of the talk, I'm going to show sort of what the specification is for the memory allocator that we're proving. But really, like, for the memory allocator, like, sort of the main thing we have to prove is that sort of memory safety holds throughout, right? Like, normally if you write a Fibonacci function, it's going to be memory safe as long as you're not using unsafe code, right? And so the only thing Verus is giving you is you're proving that just like the answer is correct. For something like the memory allocator, we're also proving that it's memory safe using sort of these techniques that I'm telling you about now. Does that answer your...
I guess it will be clearer later on, but I'm still not quite sure what Verus exactly offers, but we will see maybe later.
Right.
Thanks.
Right. Okay. Let me have to find my slide. Okay. So, right. So I guess, all right. Okay. I do have one more slide about the p-pointer API, I guess. So the four like main functions here are sort of the allocation function, deallocation, writing and reading to a pointer. And all these sort of manipulate the points to in different ways. Allocation obviously gives you a new one. Deallocation consumes it, write and read, mutate and read it. Now, again, the allocation and deallocation functions for the original p-pointer API are sort of dependent on the global allocator. But our goal with verifying a memory allocator is to implement these, right? And in general, the objective of a memory allocator is to sort of provide these alloc and free functions, which give you sort of these arbitrary allocations that are ideally like sort of, not fragmented and so on. You want to provide that API, or you want to bridge to that API from some operating system's API. For example, on Linux, you would use like the mmap syscall to allocate these like coarse-grained memory chunks that are aligned to, so like 4 kilobyte boundaries or something like that, right? So you have the allocator wants to make these coarse-grained allocations and then sort of divide it up into the allocations that the user is requesting. Okay, so you can visualize it like this. You have a virtual address space. You call mmap to sort of get some range of that virtual address space, and then you kind of divide it up. So some of this will be going towards your sort of the allocator's metadata and internal data structures, while the rest of it is going to be memory that is actually given out to the client. Okay, and so for the mimalloc design specifically, it looks like this. So this is just going to be a little bit more detail of what the previous slide was showing. So mimalloc allocates these units called segments, which are 32 megabytes. There's not going to be a quiz on this or anything, but it allocates these segments, and the segment has some segment metadata at the beginning. And then the rest of it is divided up into these units called pages, okay? And the pages also have metadata about them at the beginning of the segment. And then the pages are chunked up into blocks. And the blocks are the things that get allocated out to the user, right? So for example, these two ones I've highlighted purple could be allocated out to the client, while these other three are sort of waiting to be allocated. All right. And these are actually kept in a linked list called the free list. So the way allocation will work is it'll find your right page, your first page. It'll follow this first link from the page metadata to the first block, and it will basically give that block to the user. Pop it off the list and give it to the user. And then if it were to be freed, it would be pushed back on. Okay. And also these pages are sort of arranged in doubly linked lists, which I'm not going to talk about much because it's really complicated. But suffice it to say, to do all this sort of carving up of these segment data structures, the points to permission I showed earlier is not quite sufficient. So the first thing we need to do is we need to introduce a new ghost object, which we call points to raw. That just, instead of representing like a points to some typed T object, it just represents permission for an arbitrary subset of the address space. And what we're going to do is we're going to say that when you call into the operating system immap, so we're doing it on Linux, we're using immap. We're going to say that immap gives you sort of points to raw for the particular allocated region. Okay, so this is like essentially an assumption we're making about how immap works. We're saying that immap gives you the permissions to access this memory when you call it. And so now we have sort of two ghost objects. There's points to raw, which is permission for an arbitrary set of byte addresses. And this is just represented by a map, which maps byte addresses to bytes. And then the points to, which I showed you earlier, is sort of modeled by a pointer and a T pair. So there's a pointer and a value. Okay. And so with this in hand, once we have points to raw, and in particular, once we have this sort of assumption about immap that it gives you a points to raw object. Oh, right, sorry. The points to, there's obviously a bunch of ways you could sort of manipulate these objects. So if points to raw is representing a particular range, then you can sort of split it up into little parts and join them back together and so on. And you can also turn a points to raw into a points to T, as long as you have a memory permission for a range of memory that has the right size and alignment. Okay. So you can, if you have some like uninitialized memory somewhere, you can turn it into initialized memory for T by just writing a T there, and then you basically convert the points to raw into the points to object. So now we can basically do something like this to initialize our segment. We call immap, which will give us the points to raw permission for one of these long, like 32 megabyte chunks or whatever the size was. You kind of split it up into little pieces. So we carve off some spots at the beginning to become the segment data and page metadata, like I showed you previously, right? So we take this points to raw and we say, okay, this part of memory is now going to be typed, and we're going to put the segment header there, or the page header there. And then the rest of the sort of end of the page, or sorry, the end of the segment is going to be chunked up into pages, which become those little linked lists of blocks. Okay. Now the blocks are actually variable sized. So like each page has some specific size of block. So it could be 32 bytes or 48 byte blocks or anything. Whereas the size of the nodes in the linked list are fixed. So there are 8 bytes. So for example, if you had 32 byte blocks, you would carve out the first 8 bytes of each block to be like the linked list node. And then you would also just carry around the rest of the block as uninitialized memory. Okay. Oh, all right. I wanted to say one more thing about, wait. Right. So if the user were to say perform an allocation where we are going to pop one of these nodes off the linked list, we would take this points to node and we would take this points to raw, and then we would, so together that forms like the 32 bytes we want to give out to the user. So we would transform those into a memory permission that the user is expecting. Okay. Okay. So to recap all of that, we use points to, as before, as sort of in our original P-pointer API, to represent memory permissions for like typed, well-typed objects of type T. Whereas points to raw represents permission for untyped and uninitialized memory that can be used to represent sort of arbitrary variable size ranges. We axiomatized the function of immap via points to raw. And finally, once again, all these ghost objects are sort of conceptual proof objects that don't have any impact on runtime code. So this is another good spot to stop for questions if anyone has them.
Hey, Travis, can you have 2 points to raw that are overlapping, or do you always guarantee that they're non-overlapping?
Right. So that would be, yeah, you can't have that. Because if you did that, then you could have two people who think they have permission to the same memory.
Just confirming. Thanks.
Yeah.
Just to be sure I understand about these points row and points to, in the example you showed, there was precise values. Are those supposed to be symbolic values, or like, or does Verus do, like, because what if, for example, you do two mmap and they happen to be next to each other? Can you fusion or merge those 2 points to row together? Because how do you know that there would actually be the same, that they would be contiguous? You
right.
See what I mean?
So that is, well, yeah, so that's not something that the memory allocator needs to do. But again, any kind of reasoning like that where, oh, like there is an example where we have to like sort of fuse something together, which is where we have to like refuse, we carved off the 8 bytes for the linked list, but we have to like refuse these together when we pass it out to the user. So obviously that reasoning all has to be symbolic. So I used 24 bytes for a concrete example, but the actual code, or sorry, the actual proof code we've written doesn't write about 24 bytes. It writes about some block size, and it writes about sort of this 8 bytes at the beginning, and it writes about like the n minus 8 bytes at the end. So it's actually all symbolic.
Yeah, I can see how the Verus code is symbolic, but the Verus itself, the tool, when doing the verification, and for example, let's say there is a call to mmap. The actual address, is there an actual address, which is an actual integer, or is it the symbolic value?
Right. So when the code actually runs, obviously mmap returns a specific like pointer to a specific address.
So Verus is not a static analysis tool, it's dynamic. I thought it was a static analysis tool. So you have to run your code, you have to run Verus on a particular path of execution. It doesn't analyze
so
all.
Verus will show that for any concrete value that the operating system returns.
Okay. And to represent
the
this,
execution will be correct. So it will symbolically represent that value that's returned.
Okay, thank you.
Okay.
Merrick, go ahead.
Merrick has a question.
Hey, Travis, very nice talk so far. I just have a question about the transition from a points to row to a points to. You said earlier that you were not reasoning about alignment. So I'm just very curious, what do the preconditions look like to transition from a points to row to a points to in terms of, the size of the memory object of the type you need and the alignment requirements that you have?
Okay, yeah, so about alignment. So you're referring to this where I said to convert to a points to, you have to have the right alignment, right?
Yeah, you need the right alignment.
This is a requirement of Rust that I think it assumes that types have the right alignment and size and everything. So we, in order for our specification, in order for this whole system to be sound, we have to have this as a requirement. What what I said about alignment way at the beginning of the talk, that we don't support alignment, what I meant is that our allocator does not allow the user to specify an alignment for the allocation they want. But we have to deal with an alignment internally all the time. It's just that when the user requests something with a specific alignment, there's a bunch of logic that has to happen to make that happen, and we haven't implemented that.
But so do you also have in Rust, or rather in Verus, some kind of axiomatization of the C size of to get, the right size for a given type?
Yeah. There is a feature for reasoning about the size and alignment. What it actually does is, it's a little awkward. Basically, the developer will say, I expect this type to have this specific size and alignment. And then Verus will assume that, and then it will also check when you actually compile the program that Rust actually assigns that particular alignment. So when it compiles, it'll check that your assumptions about the size and alignment are correct.
Okay, makes sense. Thanks.
Okay. All right. Concurrency. So the memory allocator is concurrent, and this is obviously a pretty big topic. So unfortunately, I can really only scratch the surface of it. But I do want to say a couple things about it. So most of the internal data structures I've talked about they're sort of mostly thread local. Like a segment belongs to a particular thread, and when the client requests an allocation, that will be allocated from some segment that belongs to that particular thread. However, it is possible that the client calls free on a pointer that was allocated by a different thread, which makes things challenging, because now, in order to free one of these blocks, you have to manipulate some of the data on a segment belonging to another thread, which means that the segment is only mostly thread local. It's not entirely thread local. So I'll actually give a concrete example using a struct definition from the original mimalloc C code base. So this is the struct that represents the page metadata. And you can see it has all these fields. And actually, it turns out a few of them are possibly accessed by other threads. So it's actually these three here. This field called offset is a read-only thread that can be read by other fields. And then you have these two atomic variables that are accessed via atomic compare and swap. The main one is this xthread free field. And it's basically a linked list that is accessed atomically. So basically, when another thread needs to deallocate a block that belongs to one thread, it will find this xthread free field, and it will do an atomic compare and swap to push that block onto the linked list. Okay, and then much later, like the original thread will come by and pop everything off and sort of sort it out correctly. So, of course, this is from the original mimalloc C code base. It's written in C, and so the sort of ownership structure is not really apparent just looking at the type. I mean, you can kind of guess that the atomic variables are going to be accessed from another thread, but it's really not obvious that like slice offset is going to be read by another thread, for example. And there's like nothing also, there's also nothing enforcing that any of these other fields are actually not accessed by other threads. Okay, you guys all know how C works. Okay, probably. In Rust /Verus, we actually have to sort of we have to encode the ownership structure and the type. So here's the page metadata struct in the Verus version of the allocator. So we have these same three fields that are accessed by other threads. So we have this page struct, which is sort of, it's going to be shared via immutable reference across several threads, right? So all the threads can access these three fields. It can access offset in a read-only manner. It can access the two the two atomic fields, which are implemented via Rust's atomic variables. Verus does have support for doing some stuff with atomic variables. I'm unfortunately not going to have time to get into it today, but you can ask questions about it later. The thing I want to talk about is this other field inner, which has basically all the other fields that are supposed to be local to the one thread. So none of the other threads are going to be touching any of the fields in the page inner struct. These are only supposed to be accessed by the one thread that sort of, I don't want to say owns the page, but like mostly owns the page, right? And so this has to be done with interior mutability, right? And so similar to p pointer, Verus actually has a p cell, which is a permission cell. And so this cell allows us to provide interior mutability. And actually the cell is actually a wrapper around unsafe cell. And so like p pointer, in order to access this safely, we have to have an ownership tract ghost permission object similar to points to. In fact, it's also called points to. And what this means now is that you can have multiple threads that share a immutable reference to this page struct, but one thread will hold on to the points to permission to access this cell. So it's the only thread that can access the contents of page inner, and it can freely read or write to them as it sees fit. Okay, so all the linked lists that are not accessed atomically, that are just sort of accessed normally, they're in here, and they're easy for the like main thread to access them. Okay, I guess that was all I was going to say about interior mutability, so I'll stop for questions here.
I have a question.
Yeah.
Do you have to put the page inner in the page struct? Could you like split it off into a different struct and I don't know, somehow put it next to the page when you actually put it in memory?
Yeah, that's a good question. Yeah, you could do that.
Okay, I see.
That would sort of be conceptually similar to what we do.
Mm-hmm. I guess you could avoid having the p cell because you just pass the middle reference to that one field, to that one struct.
Sorry, I didn't catch that. What?
And I guess you could avoid the p cell because for that extra struct, you just can pass down a middle reference.
You're right. Yeah. If you did it that way, you could avoid the p cell because you could split the page into two, and you could share one of them and then keep the other one local. Yeah.
Okay.
I think Jonathan has a question.
Jonathan has a question.
Yeah, how do you reason about aliasing between two p cells? If it's interior mutability, do you have predicates that say equal, not equal? How do you deal with that?
Right. So like with the p pointer, there's sort of each cell has like an ID, and so each points to object is sort of associated to a particular cell by that ID. So when you access the cell, you have to prove the permission object you're using is like the right one. So you can't
permission object statically tracked by Rust's type system. Is it a mute? Is it a mute pointer, the permission object?
Yeah.
Okay. This cell is like this cell. Okay, cool. Thank you.
Yeah. Okay, so I'm going to finish up by showing you like what the sort of top level API to the allocator looks like. I hope this is large enough for you to read. So this is the function signature for malloc, and it takes 3 arguments. It takes this heap, which is just sort of a pointer to the top level thread local metadata. So this is like an object that sort of has a pointers to all the segments and so on. It has this local object, which is a struct we define to just sort of package up all the thread local ghost permissions. So for example, the points to that cell I showed you in the previous slide is in here. Other permission objects for all the linked lists and all the segment metadata and so on. That's all in this struct, and this is the ghost object. So basically you have to pass that in to do an allocation. And then of course the number of bytes to allocate. Is, I guess, sort of the main argument that the user is thinking about. Right? And then it returns a bunch of stuff too. The first thing it returns is a pointer to the new allocation. It returns the points to raw permission for the allocated memory, so the user can go ahead and use the pointer. And also this Alloc is another ghost object that sort of is the permission to call free for this particular allocation. And this is the precondition and postcondition. Obviously, I'm not going to ask you to read every line on here. Really, the most important one is this one, which says that the points to raw object that gets returned is, in fact, correctly a permission for the memory range that expected. So it's for the memory range that starts at the pointer that was returned and extends for a number of bytes equal to size. Okay. So I guess this is kind of an example of what it looks like to actually sort of reason with points to raw. You have to pass these conditions around everywhere that says like, what does the points to actually, what region does it actually correspond to? This is free. So it's basically the opposite, where you call free on a pointer and then you have to pass back in everything that you got from Alloc. So you have to pass back in the permission and you have to pass back in this deallocation token. All right. And you can see here, if you read the comment, you can see that when I was writing free, I had to deal with this the way I was trying to match what Linux does, which allows you to call free with null. So we had to write the precondition to carve out the special case for if you call it with null. Yeah, so that's sort of the top level API. I guess there's also a couple of functions for like initializing the sort of initializing the primary data structure. I'm not gonna show you. Yeah, so that's pretty much it. Once again, this is a work in progress. I guess this is the same slide I showed you before. It runs, but there are some restrictions, and the proof of correctness is close to being done. At the moment, it's about 16,000 lines of Verus code, and most of that is proof code or some kind of specification code that helps explain like what's going on. Unfortunately, it's kind of hard to actually count which lines are executable. My best guess is that like 1,000 or 2,000 lines are executable. So I'm sorry, I don't have a more precise number there. But definitely most of it is proof code. By comparison, the original mimalloc is about 10,000 lines of C, which is of course all executable. Of course, they have a lot more features than we have. They're also a lot more portable for all kinds of different platform support and everything. Verus mimalloc right now only really works on Linux and it kind of works on Mac. Running the actual verification on all this code takes about 1 minute over 4 threads, which I think is pretty decent for 16,000 lines. I wish I could tell you more about like what its performance is like, but unfortunately, because of the restrictions, it's hard to run many benchmarks right now. So hopefully it's something in a few months I might be able to say more about how their performance compares to the original. And that's it. Here's references for stuff I mentioned, the sort of paper that describes how mimalloc works, and then of course paper about Verus. Our verified allocator is not yet open source, but hopefully it will be soon. And that's it. So I can take more questions now.
Well, first I want to thank Travis for this great talk, which I think interested quite a few people. But I had a quick question to start things off. You said the verification is 97% complete. Where does that precision come from? And also, more importantly,
that's not a real number.
What is the missing 3%?
That's just my
personal
estimate about how I feel about its completeness.
I figured. Where's the last 3%, or like what is that last bit that's missing? Is it the realloc, those limitations we talked about, or are there other parts that are still missing?
No, actually, when I say the proof of correctness is almost done, that's referring to the parts that we do have implemented.
Okay.
There's like one module that has all these computations with it's this computation that will map a given allocation size to like the bin that it's in. So like if the user requests like 9 bytes, then we say, okay, we're going to give you a 12-byte allocation and go to sort of the page that has the 12-byte allocation. So we have this module that does this computation, and it's done with all these like bitwise operations, and there's just a bunch of arithmetic that needs to be proved. This is probably like this is one of the main things that's not proved yet. There's another complicated thing that needs to get fixed that I'm not going to try to explain.
Okay.
Yeah, I think really it's those two things that are sort of left outstanding.
That's good. Thanks. I'll let Daniel ask his question.
Sure.
Thanks. So it seems like a great tool. So thank you for your talk. It's very interesting. I was wondering, could you speak a bit more about your verification process? So first of all, how do you specify the code? Because of course, the ensures and require stuff, you can't just write that into Rust code. So how do you do that? And how do you then transform this to something that an SMT solver like Z3 can use? Because that's how you do it, right? You use SMT.
Yeah, so this is a question about Verus in general, right?
Yes.
Yeah. So basically, so first of all, the specifications are written in kind of pseudo Rust. So they're actually, we essentially have this transformation that will take this code where you have like this special syntax and sort of convert these into like normal Rust expressions with all these like weird annotations. And those will get type checked by Rust, and then we sort of process them and sort of, reverse engineer what it was the programmer wrote to actually get like sort of internal representations of these functions. And then we just sort of we convert those to SMT almost directly. These are meant to be written in sort of a functional style so that they can be converted fairly directly into like the SMT lib language. A function like fibo, for example, would be encoded as like for all n, fibo of n is equivalent to this definition. Yeah, there's a bit more about this in our paper if you want to check that out, about how we do the encoding. Is that what you're asking about?
Yeah, exactly. Yeah.
Right.
Just one more. So okay, so you have you actually transform Rust code to something that can be, verification condition generation. That's your process, essentially, right?
Yeah.
Okay. Yes. And the specification would be a separate file or special comments or attributes. What do you?
Right. So actually, the specification goes right here next to the code. So obviously, I sort of elided the code to make it fit in the slide, but you'd actually have the actual Rust code written here, possibly interspersed with more annotations to help the proof.
Okay.
So actually, like, the actual hard thing is sort of deleting all of the extra annotations to get like normal Rust code that doesn't have any of the junk that can be compiled. So we have a way of sort of deleting it all. It's kind of a fairly baroque, gnarly process. All right, I see. Let's move on to the next one. So Isaac.
Hi, can you hear me?
Yeah.
Okay, great. Thanks for the talk. It was really cool. I joined slightly late, so I apologize if you sort of answered this previously. But I'm really curious about, in terms of the stuff that would be this left to implement to get to feature parity with the original C allocator. Do you think that there's anything complicated ghost code-wise there, or do you think that you've sort of captured the most complicated components in your ghost structures? And it would just be the case of proving it, or sort of, doing the manual proofs.
Yeah. So I tried to stick as closely to, so even though we don't have all the features, I tried to stick as closely as possible to like the way they lay out their data. There really is one big component that's missing, which is that when a thread terminates, there's this complicated procedure to sort of clean up all its data structures. And sometimes these data structures might have outstanding allocations. So there's kind of this like, the segments go into this kind of like zombie mode where they might get like recycled by anyways. I don't really know entirely how it works yet. So there's definitely work. If I want to support all that, there's definitely work to be done to figure out the right way to represent all that, how to account for all the ghost objects and so on to get that to work. So I think that would be the big outstanding thing that would need to get figured out if I wanted to sort of reach feature parity. All right, Dominic.
Hi, thanks for the talk, very interesting. I'm not super familiar with mimalloc, but I know that other allocators sometimes make use of the fact that pointers are aligned to store specific flags in the least significant bits. Would this be possible also with like p pointers, or like basically changing the numerical value of pointers without like affecting the points to permission or anything?
Yeah, so yeah, actually that does happen. There's this one process where there's one part where we have to store some extra information in like the least significant bits of an atomic field. It's actually this thing. Oh, oops. The X thread free that I was talking about earlier, the atomic free list actually stores some special bits in its lowest order bits. Yeah, so you can do that because we just treat the address space as just integers. So you can treat an address as an integer and do funny stuff to it and then get the integer back. So we don't really track like pointer provenance for anything and just sort of assume everything from immap sort of has the same provenance.
Okay, all right, thanks.
There was one question asked in chat as well, where I need to find it again. Is it possible to write an ensure statement which ensures the non-aliasing of the result of malloc?
Right. So So a property like non-aliasing is really, it's not really captured by a single insurer statement. It's really captured by like the insurers and by like sort of the general properties of the ghost permissions, right? So if you were to call malloc twice, for example, you would get two different pointers, and you would get the points to raw ghost permissions for those pointers. So the client could say, well, I have a points to for this one pointer, and I have a points to for another, or well, I have a points to for one pointer, I have points to for a second pointer. Since I have 2 points to objects, they must be different pointers, right? This is like you can essentially invoke that property if you have 2 points to objects to show that they're disjoint. This is sort of a basically an axiom about them. Does that answer your question?
It wasn't my question, but oh yeah, it does.
Well, whoever's question it was.
Yeah. Perfect. So I think if there's any last quick questions, we'll take that. But otherwise, we're gonna bring things to a close. Oh, sorry about that. So if there are any last quick questions, from Emeric, how do you compare performance-wise with other allocators? Did you run your version of mimalloc on benchmarks? Right. So the plan is to use mimaloc's benchmark suite. They actually have a pretty nice benchmark suite that actually compares to lots of other allocators. And we actually, like I said, due to the restrictions, we can't actually run most of their benchmarks to completion. But for the few we did, I initially saw that we seem to be like 2x slow. And it's not something I've had time to sort of investigate, so I don't know. I don't really have a whole lot to say about the performance comparison right now, unfortunately. But the plan ultimately is to do a comparison using just mimaloc's benchmark suite.